to do a study with a neurologist. So it depends on the non-motor symptom. But for the motor features, this is the medications we use. Now, what happens in cases with Parkinson's is that things change. Remember, it's a neurodegenerative disease. So what starts usually as motor symptoms, non-motor symptoms, progresses. And as the disease advances, patients develop more disability. We reach to a point where we start to have what's called motor fluctuations and dyskinesia. And those are the motor complications of Parkinson's disease. At this stage, medications will stop being as helpful as the initial stage of the disease. So initially, the patient takes the medication, the symptoms improves, he still will cover till the next medication. But what happened after 10, 15 years, the dopaminergic loss is so severe. The patient doesn't have any more stores. So the level of dopamine will fluctuate based on the serum level of the medication. So it will peak and then it will drop. And this develops what's called the motor fluctuation. So symptoms improve, symptoms worse, symptoms improve, symptoms worse. And we started to give the patients more frequent doses and higher doses. And with higher doses and more frequent doses, dyskinesia developed. Okay, so the response to treatment initially, and this is what I was talking about, the dyskinesia is usually, we see it on dyskinesia. We mean by on is the medication is working, like the patient is switched on. And off is when the medication is not working, the Parkinsonian features is there, we call it an off period. So initially, during the initial stages of the disease, the patient is well controlled. So he does not have that much of the off changes or the Parkinsonian features just linked to the doses, and he doesn't have dyskinesia early on. But as the disease progresses, patients start to develop those dips that I referred to as off, and because we increase the dose, we're giving more frequent doses, the patients start to develop the dyskinesia. At this stage, medications are no longer helping. So what we go for surgical treatment as deep brain stimulation. So what deep brain stimulation does is actually it helps smooth these curves. Instead of having those bad dips and then improvement and then dip and then improvement, the patient will have a more steady, or at least within the well-controlled zone. And the dyskinesia we are able to control by changing stimuli and using specific configuration. So I'm going to show you. I think it's not working. Yeah. So this is a video of a patient, one of our patients. She has Parkinson's disease. This is when the medications are off. So the patient cannot, she was asked to stand up. We usually ask them to cross the arms across the chest and stand up. She couldn't do that. She needed help. And here she is walking, short stride length, very slow, flexed posture, which is very typical for a Parkinsonian patient. This is the patient on medication. And we asked her to stand up. As you can see, it's very quick in comparison to when she was off. Now we asked her to walk. As you can see, the velocity is better, the length of the stride is better, which is reflecting the effect of the medication. This is what we refer to as motor fluctuation, and these are the dyskinesia, which is hyperkinetic movement, so usually chorea and a combination of chorea and dystonia. And this is what we mean by dyskinesia. So when the patient reaches this stage with motor fluctuation and dyskinesia and the medication is not helping, the quality of life is bad, this is when we discuss surgical treatment. So what is deep brain stimulation? Deep brain stimulation is basically a device. It's a system. It consists of what we call IPG. It's an implantable pulse generator, similar to the pacemaker that's being usually put under the skin, just below the collarbone. It's attached to wires, and the wires are attached to the electrodes, which goes in the brain. So usually the one doing those surgeries are functional neurosurgeons. I'm a neurologist. I refer those patients to such treatment, but I don't operate on them. So what they do, what the neurosurgery do is they have a beer hole in both sides, left and right, and they put the electrodes there, and then they connect the electrodes with a wire that attach to the implantable pulse generator. Now the IPG, the implantable pulse generator, will start to give electrical stimulation. We program that to give electrical stimulation that will end up at the tip of the electrode deep in the brain, in specific areas I'm going to mention in a moment. And this is what we call the programmer. This is what we use in clinic. And this is the patient programmer, what goes with the patient to help him adjust the stimulation if needed at home according to our instruction. Usually we limit that, so we don't give the patients the freedom to do whatever they want. So it's usually limited what they can do with this machine. IPGs previously, which is the implantable pulse generator, used to be a little bit large, more square edges. Now it's more round. It's smaller, so it's better tolerated, not causing any skin. Usually they have like eruptions, and sometimes even it goes out of the skin. And also now we have rechargeable batteries. So usually the half-life or the life of the battery is 5 years for the non-rechargeable. Now with the rechargeable they can go up to 15 years. And this is important in some patients when high stimulation is needed. Also now we have more MRI compatible IPG. Before we did not have that, so patients with DDS cannot undergo any imaging that requires MRI. So where we put the electrodes? So we have here, this is it's the surgery usually. We call it part of the stereotactic surgery. Stereotaxis is basically trying to define a specific point in a 3D dimension, in a cube. So what the surgeon does is they do brain imaging, MRI, they do CT scan, they try to identify where the exact location of the deep nuclei we want to stimulate. This is tractography. Here you can see all the fibers, whether coming from the internal capsule, the one responsible for example, medial meniscus, hearing, etc. All of those are surrounding the electrodes. And this is very important because the stimulation that we give will not only affect the structure that we want to stimulate. It can spread. And so this is where side effects coming from stimulating the tracts or the fibers surrounding the area. So what usually we do to identify the deep nuclei we want to stimulate, which is for the Parkinson's disease, are two: the subthalamic nucleus and the globus pallidus interna. So what also happens in the surgery is that we do what's called intraoperative microelectrorecording, and this is by inserting an electrode that will go down the brain structures, and as it goes down, it records the electrical stimulation those structures give us. It has characteristic sounds, so there's a characteristic sound for each structure, each part, and this is also to help localize the tip of the electrode. Our favorite is usually the dorsolateral part of the subthalamic nucleus, and this is the aim. If the surgeon goes a little more ventral, side effects as psychiatric behavioral changes can happen. If they go a little bit more close to the internal capsule fibers, muscle contraction will happen when we start the stimulation or the programming. So it's important, location, 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 as we say to the neurosurgeon, because this will help us program the patient better, so the improvement will be remarkable and the side effects will be as less as possible. So the deep brain stimulation surgery is an awake surgery. We do it while the patient is awake. The patient gets a numbing agent where they have the frame. This is called a Blexel frame, and the neurosurgeon will start, again, numbing agent, and we'll start with IV sedation, and they start to insert the electrodes in both sides of the brain. Why we need the patient to be awake? To assess the response of the deep brain stimulation while the patient is under operation. For example, when we go for GPI, if the patients start to have flashes of light, it's very close to the optic tract, so we know probably we are close to the right spot. We also can observe the improvement of tremor immediately. Patients, for example, who undergo the surgery for functional problems, like, for example, playing in instruments. They usually bring their instruments and it's played in OR during the operation. After that, the patient will receive general anesthesia and the implantable pulse generator will be inserted and the wires will be connected with the electrodes on both sides. So how does DBS work? The simple answer to that, we don't know, but we have theories about that. If you ever program the patient with deep brain stimulation, they will have a tremor, and the tremor immediately will go away in clinic, which gives a good feeling for the clinician and the patient. But the mechanism to that is different, because tremor will go away immediately, the bradykinesia and rigidity will take hours to go away, and the axial symptoms will take days to go away, or months. So the variable response tells us that there's no actually one mechanism to explain how DBS works. So the one, we call it the reversible symptoms is usually caused by a reversible method, which is the modulation of pathological network, whether local or network-wide electrical and neurochemical effects of the stimulation, and the modulation of the oscillatory activity, i.e. it works on the pathological network. But the more, let's say, long-term effects that takes longer to happen, those probably happen through what's called synaptic plasticity, and this is basically a change in the synaptic transmission that happens because of the stimulation over time, which will lead eventually to have a modified brain function. Okay. So, and anatomical remodeling, this is basically, there will be a change in the area stimulated. Who are eligible? Patients with a refractory motor fluctuation and complications on the chronic levodopa therapy, refractory tremor, and patients who receive dopaminergic agents, but yet they are not doing well on the medication because they could not tolerate the side effects. However, also there are more stratified ways to deal with those patients. Disease duration. We don't accept operating on a patient with early Parkinson's disease. We usually request at least 4 years. The age should be less than 70. Patients should have levodopa responsiveness and dramatic actual levodopa responsiveness early on. And the type and severity of levodopa responsive symptoms, because the symptoms that's going to improve on deep brain stimulation are the symptoms that improves on levodopa. Cognitive and psychiatric issues are usually, especially if they were profound, are contraindication to go for deep brain stimulation. Those can get worse. And comorbid disorders, if the patient, for example, is having multiple comorbid diseases that prevent him from undergoing operation, he's not fit for surgery, then he's not going to be a candidate. And the brain MRI findings, patients with severe atrophy, with multiple white matter changes, severe white matter disease, they may not benefit, or the surgical risk is high for those patients. So the path to surgery is usually through a multidisciplinary team, movement disorders, the neurosurgeon, a neuropsychiatrist for a pre-op assessment, a neuropsychologist for more detailed cognitive assessment, and the patient and family, we do good counseling. Just going to show you a patient with after deep brain stimulation. So he's having refractory tremor, and as you can see, after deep brain stimulation, tremor is improved significantly. Okay, I'm done almost. Targets, so that's it. So the targets, we have the two targets, as I've mentioned, the subthalamic nucleus and globus pallidus interna. And this is a study in 2001 published in New England Journal of Medicine that looked into both targets. And as you can see here, the improvement in the off period from 49% reduction to 19% at 6 months of DBS surgery, the on without dyskinesia from 27 to 74%. Improvement in the on period, which is remarkable, and the same probably percentages for the GPI. Long-term effect persisted, so even at 5 years follow-up after this study, patient still have improvement on those symptoms, but the symptoms that did not improve are the actually akinesia, speech, postural instability, and gait that did not improve while the patient is on medication. So, again, the symptoms usually that improves is the one that improves with medication. I'm going to finish here. DBS versus the best medical therapy. We know that for patients on advanced stages, DBS actually works better than DBS. If you can see here, this is a scale for the quality of life. This is a systematic review and meta-analysis that was done where 8 eligible randomized control trials were included, and we found that the significant improvements in UPDRS, the PTQ 39, and the LED score were in favor of DBS. However, as you can imagine, the adverse events, however, were not in favor of DBS. It was in favor of the best medical therapy. And early versus late, this also systematic review looked for patients who received it early at the early stage of Parkinson and a late stage of Parkinson, and they found that there is no difference between the two. There is actually no favorite. GPI or SCN, both can work for the patient, and the decision is made based on what's called precision medicine, tailored to the patient's individual case. What's the symptoms the patient is having? What are the side effects? This is how usually it is. Thank you.
Thank you, Dr. Taha, for this simplified but thorough as well presentation. I think Dr. Taha will be happy to answer any question if you have. Yes, Dr. Salim.
What are the backdraws of actual surgery? So the chances of infection and how you balance that with the slide.
So yes, there are surgical complications, and this is actually with intracranial hemorrhage, about 4.4%. This is actually lesser in more expertise medical centers, as you can imagine, because it depends also on the surgeon ability to implant the electrode with the least damage. Infection is the highest, probably most common side effect because, again, it's a foreign body in the brain, so it's about 5.1%. And there are also what we call stimulation-related side effects. Speech is one of the major, unfortunately, obstacle for patients going to DBS because it may get worse. Surprisingly, weight gain, which people can consider as a side effect, some people may not consider a side effect, and this happens because dyskinesia lessens. So the patient does not have those excessive movements anymore all the time of the day. Also, their mood improves sometimes because their motor symptoms improve, so they have better appetite in comparison to how it were before surgery.
Any question? Yes, please.
Sorry, Yes. So this is what. Yes. So this is what I saw. What I told you about here is that the meta-analysis here and systematic review looked at that, and the adverse events in cases of DBS is more than the best medical therapy for the obvious reasons.
I don't think we can take any further question because of the limitation in time. Let's switch gears a little bit. So we have Dr. Sirine Atinami, who is Assistant Professor at Princess Sumaya University and the Head of Data Science Department at Princess Sumaya and at King Hussein School of Computing Science Faculty. So welcome, Dr. Sirine.
مساء الخير، كيفكم؟ اسمي سيرين عطياني، أنا أسيستنت بروفيسور زي ما قدمت دكتورة بجامعة الأردنيه. قسم الداتا ساينس، احنا we have a program هو data science و artificial intelligence. وماي background is a mix between the two. فأنا I come from a bachelor's in computers and master's in computer science and a PhD in neuroscience. So تخصصي الدقيق هو computational neuroscience. So I studied the brain in order to model the functional activity. يعني كيف, how do we hear, how do we perceive, how do we learn. We've used AI, our techniques of AI in our research in order to decode signals in the brain. Currently we're using AI in order to help with applications in neurology, applications in neuroscience. بالنسبة لنا خصوصا أنا جاي من يعني I have a leg in both fields. I feel that both fields بيرفضوا بعض. يعني one field gives information about how the brain functions. The community in computer science strives and have striven for a very long time to mimic human intelligence. So we try to learn how the brain does it, and then we incorporate it into algorithms that in turn it comes a full circle to help us in understanding how the brain functions and help in applications in neurology. So we don't delay further. AI has been part of, or for the last 10 or 20 years, part of the healthcare industry, and more so after the explosion of clinical data in the healthcare field. Now, as humans, we're generating huge amounts of data, and the healthcare industry is not immune to that. We have an explosion of patients' data, so I'm نحكي عن the history of the patient, about the history of medication. We have imaging data, and now we can store them without limitations. Now we have unlimited storage, so we have an explosion of imaging data, CT scans, MRIs, X-rays, وهكذا. We have genomic data that we are tapping into in order to understand the patient more, understand what medical applications will or treatment is beneficial to this patient as opposed to other patient in the field of precision medicine. And there's also huge data that's being generated in the pharmaceutical industry about interactions. So أنا عم نحكي interactions between chemical substance or interactions between these chemical substance and humans or animals. So the use of AI in clinical data is pushing the boundaries of science. Again, it's this circle. It's never one field applied to the other for the benefit of the second one, but it's also the full circle that I mentioned in the beginning. So we're seeing machine learning is one of the subfields of artificial intelligence being used for retina images to enable health screening for the eye diseases. We're seeing description of logic to organize health data with the clinical terminologies. We're seeing machine learning again used to understand the movement patterns of aged بهاي الحالة كانوا Australians. We can see cloud computing being used in order to analyze genomics, in order to come up with detailed sequences, and natural language processing being used to extract specific reports. But also in the field of neurology, we have the use of deep learning to analyze brain images. And I'm going to talk about, for example, in neurology, which is how AI is being applied in neurodegenerative diseases, how it's being applied to help with neuro-oncology, with neurovascular conditions, and with spinal cord injuries. There are many applications in neurodevelopmental diseases or disorders, and also in the understanding of basic functional properties of the brain, which will I come back to at the end of my talk. So in the case of neurodegenerative disease, I have two examples to tell you about. One of them is using semi-supervised machine learning to isolate MRI biomarkers. So what are the biomarkers that we can find in an MRI that will tell us, will give us an indication of this person has a higher likelihood than the next person, if they have an MCI, a mild cognitive impairment, to progress into Alzheimer's disease, la samhallah, right? So what are these biomarkers? Because we see المشكلة with Alzheimer's disease, as you know more than I do, is that الضمور اللي بيصير بالدماغ هو أحيانا جزء منه related to age. So how do you distinguish between some sort of pathologies موجودين بالMRI? What parts of these are regular and what parts of those are pathological, and they need to be tracked because they are likely indicators of progression to Alzheimer's disease. The other example is using AI algorithms to find places for brain atrophy, where those atrophies are and how they develop into Alzheimer's disease. So what they do is that they take, in the first study, they took the MRIs, they isolated the biomarkers, as you can see. This is a description, a flowchart of the system. And after isolating the biomarkers, they took the age and the cognitive conditions of the patient. Because if the patient at the beginning of, when people notice the condition, if they are already at a certain level of cognitive impairment, you need to adjust that in order to measure the progression of the impairment, how does it progress, and then whether it develops into Alzheimer's or not. So using these two measures, biomarkers from the MRI, information from about age and cognitive measures, they were able to estimate, they were able to predict with a 90% accuracy whether that patient is going to progress from mild cognitive impairment, which almost all Alzheimer's disease patients are diagnosed with in the beginning, into an actual full-fledged Alzheimer condition, which will appear with age, but will appear after many, many, many years. Another example, which is with the Parkinson's disease. Parkinson's, what they did, there are two studies. One of them used handwriting. So they took a tablet, as you can see here, and based on the grip on the pen, the angle of the pen, and how they drew, they passed that drawing into a neural network, an artificial neural network, and based on the angles, the angle of the hand, the grip, and the firmness of the grip of the hand, they were able to predict the progression of Parkinson's and whether this person has Parkinson's or not. The other system was using speech. So they took recorded speech from Parkinson's patients, and using also, trying to isolate speech features, and feeding that into an artificially intelligent system, they were able to classify the patients as having Parkinson's and the degree of the disease. In neuro-oncology, MRI has been used in order to detect and localize a brain tumor in early stages and in late stages, and that helps with the surgery. And what happens is that they took MRI images, and through using a technique we call image segmentation, this is something that the radiologist looks at, and by looking at it, they can actually do it by eye. We need an artificial intelligence system to do it automatically. So taking the MRI images, feeding those with labels. So we have historical data that says this patient has a tumor in this location, this patient doesn't. We feed them into an artificial neural network, and that neural network, which by the way is built based on the structure of the neurons in the brain, that artificial neural network can segment these MRI images into different sections, and based on that segmentation, they can isolate a tumor and define the contours of the tumor, return it to the oncologist as a 3D object. In neurovascular condition, AI has been used in studies to help detect early warning signs of ischemia on CT images, to measure the extent of early ischemic changes, and to detect also blood clots following strokes. So using fully automatic systems, the fully automatic detection, the system is able here to isolate locations of blood clot. Also in AI and spinal cord injury, this study from 2016 was able to allow, and it's really exciting, was able to allow a quadriplegic patient to reconnect. He's paralyzed, right? He has a spinal cord injury from right here, using imagined movement. So they asked the patient, using imagined movement, to imagine the movement. So play the guitar, it's a guitar game here. And to imagine movements of his hands, arms, to actually move the guitar, using those signals from the brain for imagined movement. They were able to decode those signals, those firing activity from motor cortex, and then use that in order to feed it into the arms, like the fibers, the nerve fibers into his arms, and he was able, with training, to move, right? So that, bypassing the spinal cord injury, because the nerves still are alive and well, they were able to do that by decoding the signal and decoding the transfer that happens naturally through the spinal cord in order to allow this patient to move his arms again. What they used is something we call principal component analysis, and it's a technique, it's an unsupervised learning technique that we use sometimes for dimensionality reduction, but also sometimes for separating different sources that are not, let's say, that they're not trivially seen or visualized. The background to this is, and now I'm going to jump into neuroscience. This is my field of work. Is the reason they knew how to do this is because neuroscientists have studied movement, motor movement, and one of the problems, and this is a study by Churchland in 2012, one of the problems is that, okay, so you have an arm movement for like a monkey here, and at the onset of the movement you have a dip. You get another set of movements here, and sometimes it's a peak, sometimes it's a dip. We don't know, hold on, there's a, okay. Sometimes it's a peak, as you can see here, sometimes it's a dip. And for a long time, people did not understand why are primary motor neurons firing in the way they do. It does not depend on the activity, it does not depend on the angle, it does not depend on the reach, right? It changes, right? So why do we sometimes get a peak? Why do we sometimes get a dip? That was not understandable until they tried to analyze, again, these sets of neural signals using principal component analysis, and were able to, I'm sorry, and hon, for some reason this is here. No. Okay, I was going to show you the individual principal components. Yes, it did not transfer from to this computer. Anyway, it's fine. So they were able to isolate separate principal components that showed that primary motor neurons work as a dynamic system. They don't indicate that I'm going to move right now. They don't indicate that I'm going to move with this angle, because our motion is a continuous, right? I start moving now, but I'm continuing my movement, and my movement is not jerky, right? So I'm not moving like a robot. I'm moving a continuous movement. It's a dynamic system. So actually motor neuron sends the signal to start the motion. And you have a whole lot of systems, including the spinal cord, including the other parts of the brain that actually contribute. It's a whole system that contributes to the movement, but primary motor neurons work as a dynamic system. That was a pretext to the spinal cord injury study that I told you about. I'm going to tell you finally about one more study, and that's more related to what I do. I do auditory neuroscience. We studied auditory neurons and how do we actually hear, what happens in primary auditory cortex, how do we attend to sound, what's the difference between our primary auditory cortex attending to a sound versus when we are sitting idly not listening, right? What happens in our brain? And a follow-up to that, to the work that we did was a study by one of my colleagues, Ms. Garani et al. He's currently at Columbia, where he actually implanted a set of ECOGs. Here you can see patients with epilepsy who go in order to monitor them to see where the implant for the relief of the epilepsy sessions happen. They sit with a set of ECOGs on top of the brain. They have a surgery, they open their brain, and then they put a set of ECOGs, usually around temporal cortex, which is very convenient for us because that's what we want to study. So he located he put those ECOGs, and he can monitor activity from the top of the temporal cortex. And what the experiment was that we give the patients two speakers. One speaker that says, ready tiger, go to green 5 now, and another speaker that says, ready Ringo, go to red 2 now, right? If every speaker is speaking on their own, it's easy to listen and you can understand them. But the thing is, we don't give them together, we give them on top of each other. As you can see when you are sitting in a session where 2-3 people are talking. This is a regular thing, our brain solves this problem easily with no problems. So how does our brain solve this problem? When this is the spectrogram, when the two speakers are on top of each other. Our brain, it turns out that when we attend to one of the speakers versus the next one, we are actually increasing the gain, increasing the gain of the neurons that are actually responding to the first speaker, and we are suppressing the response of the neurons that are not listening, that are listening to the other speakers, that are tuned to the features of the other speaker, right? So, and there's the difference in this study between when you're listening to the second speaker alone versus when you're listening to them together while attending to that speaker, and when you're listening to the first speaker alone, the dashed red line, or the second speaker when you're attending to the first speaker. So what they did is that they took this finding. They took this finding and they fed it into an artificial neural network, and that artificial neural network separates the two speakers. Okay, so the two speakers, the two speeches, the sound stream is separated using the neural network. Then they take feedback by taking an implant on top of the skull here, right, non-invasive. That actually, just like an EEG, takes the brain signals and isolates the brain signals, and through that they can attest which one they're attending, this person is attending to. And then using the feedback from the brain, it feeds it back into the neural network to amplify the sound of the person you're interested in listening to. And this is currently being implanted and being incorporated with the assistance of Nautica, which is a hearing aid company in the Netherlands. Food for thought, which is what I told you in the beginning, that early AI development is inextricably intertwined with neuroscience. Many of the pioneers straddled both fields: Hebb, Hinton, Hopfield, McCullough, Pitt, and Turing. Even Turing, the father of the computing machine, was dreaming of an artificially intelligent system. AI methods and algorithms have been instrumental in driving neuroscience discoveries and breakthroughs and support development of new diagnostic and treatment tools in neurology. And neuroscience discoveries in turn fuel new generation of AI methods and systems. For example, the new techniques that we're actually now using and studying, like the elastic weight consolidation algorithm, it is inspired by continual learning in the brain. Differential neural computer is inspired by the working memory formation of learning. Experience replay in deep Q networks is inspired by the hippocampus function. and selective attentional approach to scanning input also is inspiring new algorithms. One last thing to tell you and to leave you with is that global artificial intelligence in neurology market is expected to grow at 41%. This is from a study that has been published recently by this company. It's called Market Intel. It tracks different fields of the market and different industries and which one have likelihood to grow. So between 2021 to 2026, this market is expected to grow by 41%. And thank you for listening.
Thank you, Dr. Serene, for shedding some lights on this interesting evolving topic. And we can have a single quick question. Yes, please.
عندي سؤال. هلا ال AI بشكل عام فاهمه بشكل اساسي هو عن recognizing patterns. ممكن الفيزيشنز او الراديولوجيست او حتى الساينتست اللي برمج ال AI نفسه لو طلع على الداتا ما يفهمها وما يقدر يميزها. طب هلا بروفيسور على ايام البانديميك بالكورونا سمعنا عن ريبورتس عن AI اب على التليفون مش حتى اكسبنسيف ماشينري، طبعا السوفت وير اكسبنسيف بس تقنيه عاديه ممكن يصور صور الاكس راي ويميز بعض الامراض احسن من الراديولوجيست بنسبه كبيره. يعني الراديولوجيست بنسبه 78% كان الرقم والاي اي اكثر من باواخر الثمانينات. وجهه نظرك بروفيسور من وجهه يعني من الاي اي ومن الكمبيوتر ساينس، ايش رايك هذا راح ياثر او راح يغير في المنظومه الصحيه او في الاختصاصات حتى من هون ل 20 سنه قادمه؟
هلا بالتأكيد every time automation goes into a field there is job losses that happen, right? اللي بيصير إنه more specialized individuals are needed. More specialized individuals are needed in order to control for the machine systems that are being deployed, right? So you no longer will need so many radiologists, but you will need people who will know so much about radiology and artificial intelligence and computers in order to control, because these are systems and they're bound to fail. And when they fail, you need somebody who understands what's happening and what's failing, right? So a new direction. And in our field, in the data science field, it has created a space for a lot of people, because data science in healthcare is very different than data science in the pharmaceutical industry. It's very different than data science in the banking industry, right? You need field knowledge in order to write and develop good solutions there. So a lot of what people are doing is repurposing their work and their knowledge in the field that they're working in into and acquiring understanding of new technologies in order to stay up to speed about that. Did I answer you? Thank
you, Dr. Serene. And I'm happy to introduce Dr. Omar Rawashdeh, who is a PhD holder of clinical neurology from Nottingham University in UK, and he's currently an associate professor in the Department of Anatomy and Histology at Mؤتمر University, and he is Jordanian boarded in clinical neurology. So welcome, Dr. Omar.
أنا دكتور عمر رواشدي Associate Professor in Neurology at Mؤتمر University. My field of interest is neuroinflammation, mainly in the spinal cord. And I have been asked to present something in this conference, so something interesting. So we came out with this topic, role of vaccination in Alzheimer's disease. So I have been looking for the last 2 weeks in this topic, and it seems to be promising and interesting. But before we start with this, we have to understand the pathophysiology of Alzheimer's disease. And before this, we should know how important is Alzheimer's disease. So it's the most common cause of dementia. It's incurable disease, and it is progressive disease, neurodegenerative disease, and about 50 million worldwide are affected with Alzheimer's disease. And till now, we don't have any treatment for Alzheimer's disease. The risk of dying of Alzheimer's is also increasing, probably because of increasing age of population and other diseases other than Alzheimer's disease, which carry high risk, are being treated now. So that's why Alzheimer's disease is important to treat. So what do we know about Alzheimer's disease pathology? It's a neurodegenerative disease where we have accumulation of what we call neurofibrillary tangles and senile plaques or amyloid plaques. For normal healthy neurons to work, to function normally, they should have the cell body connected to the axon terminal here through these axons, through this axon, okay? We have microtubules in these axons, from the cell body down to the axonal terminal. These microtubules carry signals and nutrients. And this is important for the survival of the neuron and for the function of the neuron. So if you cut an axon, for example, it will degenerate by something called anterograde degeneration or Wallerian degeneration. It will degenerate in 7 days because it will no longer receive signals from the cell body and the nutrients as well. So these microtubules, as in this here, okay, they are stabilized by another protein called tau protein, which stabilizes these microtubules. If this protein wasn't functioning, these microtubules usually degenerate. And as a result, the axon will degenerate. And the synapses will degenerate. And also, the cell body may degenerate by something called retrograde degeneration, which is delayed. It takes years for the cell body to die if you cut its axon. But usually, at the end, the cell body will degenerate. So this will usually create what's called neurofibrillary tangles inside the body because of the degeneration of the microtubule inside the cell body. And another histopathological finding in Alzheimer's disease is senile plaques or amyloid plaques. If you can see in this here, the amyloid precursor protein, which is inactive protein, a precursor protein. It's a transmembrane protein, if you can see. This protein usually cleaved, and it seems to be continuously cleaved by enzymes. But if it was cleaved at a certain point, it will create beta amyloid, which is a harmful protein that accumulates outside the body, leading to senile plaques that we see extracellularly. Okay? Usually, if you cut this amyloid precursor protein at 0.40 amino acid or 42, it usually produce a harmful beta amyloid protein. This is what we can see in Alzheimer's disease. Is inside the cell we can see this blue, the neurofibrillary tangles, and outside are the senile plaques, which is formed of beta amyloid and other constituents from the neuropil or the extracellular space. So currently, how do we manage patients with Alzheimer's disease? We don't actually treat them. We offer some modulatory chemicals that modulates neurotransmitters, acetylcholine, cholinesterase inhibitors, and methyl D-aspartate antagonists. And these don't usually affect the pathophysiology of the disease itself. They don't prevent accumulation of neurofibrillary tangles or senile plaques, but they produce temporary improvement in patient symptoms, transient, and it's usually modest, not significant improvement in cognition in these patients, but the actual process is progressing. So, what's the role of vaccinations in Alzheimer's disease? It started when they noticed that patients who received influenza vaccine have a reduced risk of Alzheimer's disease. So, it can have a protective role in patients with Alzheimer's disease. Another point, important point, when they found two genes, autosomal dominant mutation in amyloid precursor protein that usually cause early onset Alzheimer's disease. So they linked the amyloid, or they confirmed the relation between Alzheimer's disease and the amyloid or the beta amyloid. But it's only found in almost 5% of patients of Alzheimer's disease. Most patients, most cases are sporadic rather than inherited. But these genes, these mutations are present, presenilin 1 and 2. So this is the widely accepted hypothesis about development of Alzheimer's disease is this problem with amyloid, okay, beta amyloid. I could not find any mutations, to my knowledge, in tau protein, so they think that hyperphosphorylated protein is a result from this, from the problem of the amyloid protein, and this created a cascade reaction that leads to hyperphosphorylated tau protein that cause instability of microtubules. So so the main mechanism or the main principle of immunization in Alzheimer's disease is to stimulate the immune system to create antibodies that can be against either amyloid or tau protein and prevent accumulation of plaques and neurofibrillary tangles, or even not only to prevent them, even to clear the existing changes, pathological changes, in an attempt to hopefully improve symptoms in patients with Alzheimer's disease. So some of these vaccinations have been developed against amyloid, while others against misfolded tau protein. So, and a number of antibodies have been investigated. We have also passive immunity, okay? This is just one slide about passive immunity, where we produce monoclonal antibodies against beta amyloid, and many of these are being investigated, and one of them has been approved, which is aducanumab, okay? The main thing here in this lecture is the active immunization in Alzheimer's disease, where we produce antigen that will stimulate the production of polyclonal antibodies against either amyloid or tau protein. Initially, these antigens will stimulate beta cells and T cells. I could find under this topic, I could find 856 results on PubMed with using the keyword Alzheimer and vaccination, including all type of results. And until 220, there were 140 vaccination reports of antigens against beta amyloid and 25 against tau protein. So extensive research is being carried out on this topic. 3 minutes. So I will go through some of these vaccines. Most of them are in the clinical trials. So we don't have very much access on details about these, the results of this. But we'll speak about some old clinical trials. In 2001, the first one was AM1792 was tried, and it was able to clear most of the most of the amyloid plaques from the extracellular parenchyma, and but the study was terminated because of development of aseptic T-cell meningoencephalitis. Probably because of stimulation of T-cell mediated, or because it produces polyclonal antibodies, and it also stimulated or activated the T-cells, and this created this meningoencephalitis, so it was terminated. But it was very useful study. 2 patients who died 14 years after that, and they did post-mortem study, and they found significant reduction in amyloid plaques, but extensive neurofibrillary tangles. They could not prevent formation of neurofibrillary tangles. Okay, the study encouraged others to, because it cleared most of the amyloid plaques. So they try to produce more specific antigens, and not using the full-length beta amyloid protein antigen. So subsequent studies created more specific. These are some of these vaccines. ACC001. It did not show statistically significant results. CAD106 has been terminated by Novartis, although it showed safety. It was safe and tolerable for patients. And these are other other vaccines. All of them are against amyloid or beta amyloid. This is a vaccine is being investigated in clinical trial phase 2, AVAC1, and it shows promising results, hopefully. So what we conclude from this is that technically vaccination procedures appear to be feasible as a treatment choice for Alzheimer's disease. Almost 160 vaccines were tested, but none of them is FDA approved until now. Many of these trials have been terminated for many reasons. Maybe because of inappropriate pathological targets, maybe our hypothesis is not right, maybe there is a defect in the immunotherapeutic procedures that we do, we don't understand the immunological process, and maybe problems with the clinical trial designs. And thank you.
Thank you, Dr. Omar, for this presentation. And I'm sorry, I don't think that we have time for questions. Thank you. So now we will start the student session. I think your battery is empty now, and this is the last session before the lunch break to recharge your batteries. So we have here Asil Badwan, who is a third-year medical student at Jordan University. Fourth year? It's written here third, so fourth year, sorry. And she is going to present a research which is supervised by Dr. Mahmoud Abdulla, who is a neurosurgeon at Jordan University. Welcome, Asil.
يعطيكم العافية جميعا. هسه راح تبلش فقرة الأورال بريزنتيشنز، بس زي ما بتعرفوا في جائزة للبيست أورال بريزنتيشنز لكل سبيشاليتي. هسه احنا بالنيورولوجي فهسه كل واحد فيكم راح يصوت على البيست أورال بريزنتيشن اللي بشوفه مناسب. حيكون عبارة عن فورم، لما تدخلوا عليه حتشوفوا انه مثلا اول بريزنتيشنز من تقريبا من 1 ل 10 بتصوتوا انتم شو اللي بتشوفوه مناسب. هسه بعد نهايه كل بريزنتيشن راح نطلع لكم كيو ار كود. هذا الكيو ار كود تعملوا له سكان، بتفوتوا على الفورم، اول بريزنتيشن بتلاقوه عندكم على الفورم بتصوتوا عليه وبوصلنا النتائج عشان بعدين نطلع احنا احسن اورال بريزنتيشن. يعطيكم العافيه. خلال 1 مينت التصويت راح يكون، بعدين راح نسكر الفورم. تمام؟
Hi everyone. قصتنا لليوم بلشت بال 2012. كان في صبية اسمها فرح وكانت عايشة حياتها بصورة طبيعية. تزوجت وصار عندها بيبي، بس بيوم من الأيام صحيت مو قادرة تمشي. راحت على الدكتور وخبرها إنه بعد هذا اليوم ما رح تقدر تمشي إلا بمساعدة عكاز أو حتى ويل شير. فرح بيوم من الأيام ممكن تكون أنا أو أنتي أو حتى هو. تخيل حالك كل يوم بدك تصحى من النوم بدك تفكر مليون مرة كيف بدك تطلع على شغلك أو جامعتك. طب تخيل حالك تخسر وظيفتك اللي طول حياتك عم تشتغل عشان توصل لها ببساطة لأنك مو قادر تمشي. تخيل حالك طفل أكبر حلم إنك تلعب مثل الأشخاص اللي بعمرك. هدول الناس الديسابيليتي ما خسرتهم بس قدرتهم على المشي، هي حولت حياتهم لرماد. هم أشخاص مثلي ومثلك ومثله عندهم أحلام، بس أحلامهم كتير بسيطة. حلمهم الوحيد إنهم يمشوا. كلمة لمتى صارت بالنسبة لهم عبارة عن إبرة مخدر بتخليهم ينسوا وبيصحوا على نفس الحقيقة، حقيقة إنهم عاجزين. إحنا بنين اليوم جايين لنعطيهم إبرة مخدر، بس هالإبرة فيها جرعة أمل رح تصحيهم على حقيقة جديدة، حقيقة إنهم قادرين يمشوا. فريق بنين اتشكل بال 2022 تحت إشراف الدكتور محمود العبدالله من قسم جراحة الدماغ والأعصاب في مستشفى الجامعة الأردنية، مكون من عبد الرحمن ميكاترونكس وإسلام ميكاترونكس وحلا يوسف هندسة صناعية ومنار عيد هندسة طبية، وأنا أسيل بدوان سنة رابعة طب في الجامعة الأردنية. فريق بنين هدفه يساعد المرضى اللي عندهم فوت دروب انهم يرجعوا يمشوا. طب شو هو الفوت دروب؟ البيشنت اللي عنده فوت دروب ما بيقدر يعمل حركة الدورسفليكشن بسبب الانجري للكومون بيرونيال نير اللي بيغذي mainly الدورسفليكسرز اوف ذا ليج، mainly الانتيريور تيبياليس ماسل. هاي الجين سايكل الطبيعية لأي شخص طبيعي مكونة من different phases، وهدول المين 3 phases. البيشنت اللي عنده فوت دروب بيكون عنده دمج بالكونتاكت فيز، وبالتالي كل الجيت سايكل عنده رح تتأثر. الديفايس تبعنا رح يستهدف هاي الكونتاكت فيز ويرجعها طبيعية بحيث انه البيشنت يرجع يمشي طبيعي as normal as possible. أسباب الفوت دروب كثيرة، وبناء على بحثنا اكتشفنا انه من كثر الأسباب فعليا بكل ارتكل عم بقرأها بكتشف انه في سبب للفوت دروب، which mean إنه هاي الكيس كتير common. أشهرها التروما أو الأكسيدنت أو حتى الستروك. ومينلي في كتير أمراض من CNS زي المالتيبل سكليروسيس التصلب اللويحي ممكن يعمل فوت دروب. Next. في أحد الارتكلز اللي قرأتها كانت الصدمة إنه الكوفيد 19 ممكن يعمل فوت دروب عن طريق الانتراكشن between الفيروس itself والاميون سيستم، بالإضافة إلى الانفلاماتوري بروسيس and نيرفلسي ممكن تؤدي إلى حدوث الفوت دروب عند هدول البيشنت. For 40% من مرضى الستروك ممكن يصير عندهم foot drop, which mean إنه الحالة جد كمان and we should take an action. Next. الحل. Our new intelligent solution, which is Pinin device with Pinin mobile application. Pinin device هو عبارة عن functional electrical stimulator بيبعث electrical pulses كبديل للسيالات العصبية اللي المفروض تنبعث من الcommon pylonial nerve. هاي electrical pulses رح تروح على paralyzed muscle, which is mainly anterior tibialis in case of foot drop, تعمل لها تحفيز ويصير الcontraction, ترتفع القدم, which is dorsiflexion, فبيمشي المريض. Pinin device is a medical cuff بينحط بموقع العصب التالف وبيعمل على إرسال الإشارات العصبية فبتصير dorsiflexion. Above the intensity, البيشنت رح يحتاج على الأقل إنه يزور الدكتور مرة واحدة من أول مرة اشترى فيها ديفايس عشان الدكتور يحدد لهذا البيشنت النورمال فاليو أو النورمال رينج اللي بيقدر يحدد فيها الانتنسيتي. والفيجن تبعتنا إنه يصير الديفايس تبعنا يحدد هاي الانتنسيتي لحاله بدون الحاجة لزيارة الدكتور. رح أحكي لكم عنها كمان شوي. Next. Pinin device. الكومبوننتس تبعونه هو عبارة عن simulating unit مسؤولة إنها تعطي الإلكتريكال pulses اللي رح تنتقل عن طريق الوايرز إلى الإلكترود والإلكترود بدوره رح يوصلها إلى السكن ومن ثم من السكن إلى المسل بيصير الكونتراكشن which is dorsiflexion. Again. Okay. Pinin application. This is the new in our device. Pinin application بيوفر خواص مش موجودة ولا بأي application من النوع هذا اللي هي مشبوكة مع devices تعتمد على functional electrical stimulation اللي هو أصلاً موجود بس application لديفايس اسمه باينس وكانت الريفيو عليه كتير سيئة. بالنسبة للخواص لا الجاي. الخواص تبعت Pinin application. اوكي في المود هون الديفايس نفسه رح يحدد المود تبعت البيشنت. مثلا في الاوتو مود بحيث انه ديفايس لحاله رح يحدد اذا هذا البيشنت هلا عم يمشي او هو واقف وبناء عليه رح يقرر الديفايس اذا رح يبعث الكتريكال بلسز ولا لا. بالاضافه الى الستاند باي انه ديفايس لحاله رح يعمل بوز لما البيشنت يوقف ويبطل يمشي. اما بالنسبه للهابت تراكر فهاي الخاصيه as we know انه اغلب البيشنت اللي عندهم مالتيبل سكليروسس رح يحتاجوا الى مجموعه من الهبت زي مثلا ياكلوا وجبات معينه او يلعبوا رياضات معينه بوقت معين. وظيفه الابلكيشن تبعنا انه يبعث زي نوتيفيكيشن لهذا البيشنت بالوقت اللي لازم ياكل هاي الوجبه او يعمل هاي الهبت. اما بالنسبه للباتري فلما ينخفض الشحن تبع الديفايس رح يوصل البيشنت نوتيفيكيشن انه هلا لازم تشحن الديفايس. اما الانتنسيتي مثل ما خبرتكم انه الدكتور رح يحددها للبيشنت خلال اول زياره ورح نطور عليها بادخال الاي اي وهلا رح احكي لكم عنها. Next. ايش دور الاي اي؟ This is our new and our device which is Pinin. وظيفة الاي اي انه ياخذ داتا من الاجر السليمه ونطبق هاي الداتا بالاجر التالفه بحيث تكون الكونتراكشن which is dorsiflexion as accurate as possible وتصير بالضبط نفس الاجر السليمه. بالاضافه الى الانتنسيتي اللي البيشنت رح يبطل يحتاج انه يزور الطبيب عشان يحدد هاي الانتنسيتي. حيصير الديفايس بناء على الداتا اللي حياخذها من هذا البيشنت من القدم السليمه يحدد الانتنسيتي that is customized لهذا البيشنت. اما بالنسبه للريسيرش اند ديفلوبمنت بيربسز فمن خلال بحثنا توصلنا انه جد الاسباب تبعت الفوت دروب كثيره واحنا هدفنا انه نحصي هاي الاسباب قد ما نقدر عشان نقدر نوصل لكل البيشنتس اللي عندهم فوت دروب بالعالم. Next. Why Pinin? Pinin يعتبر الجهاز الاول اللي بيعتمد على الفانكشنال الكتريكال ستيميوليشن بالاردن، صناعه اردنيه محليه. بالاضافه الى Pinin ابلكيشن اللي مش متوفر ابدا ابلكيشن مرتبط مع هدول الديفايسز بيوفر الخواص اللي بيمثلها Pinin ابلكيشن. ورؤيتنا انه نعمل انتجريشن بين الاي اي مع Pinin ديفايس بحيث انه تكون الكونتراكشن as accurate as possible. Next. بالنسبه للتكنيكال سايز at this stage الديفايس تبعنا قدر يحدد البوينت بالضبط اللي عم بيصير عندها الدورسفليكشن. لما تتحدد هاي البوينت رح يعطي زي سيجنال، ممكن تكون عبارة عن لايت بلب أو ممكن تكون عبارة عن ساوند. طبعا وصلنا لهاي النتيجة نتيجة إنه ما كان عندنا funding نقدر نجيب efficient components يساعدونا إنه نعمل الdorsiflexion. But as we received funds from different organizations, now we are working إنه إحنا نستخدم more efficient components بحيث إنه تستبدل هاي السيجنال بريل dorsiflexion أو بريل contraction. Next. إيش هم الavailable solutions اللي بيستخدموهم البيشنتس اللي عندهم فوت دروب بالعالم؟ 80% من البيشنتس عم يستخدموا الآفو، له كتير disadvantages أهمها إنه بيعمل irritation بالإجر، بلس إنه البيشنت ما رح يقدر يلبس البوت تبعه إذا استخدم الآفو. أما ثاني واحد فهو every way. ليه هو سيء؟ لأنه it's not compact as one unit. يعني البيشنت بيكون حاطط الديفايس بجيبته والديفايس مربوط مع أسلاك للقدم. أما بالنسبة لبينس بيتراوح سعره من 7000 إلى 8000 دولار أمريكي، بالإضافة إنه بينس حاولوا يعملوا أبليكيشن وهذا الأبليكيشن كانت ريفيوز عليه كتير سيئة فلغوه. Next. Next. About our research. Now بمستشفى الجامعة الأردنية بقسم جراحة الدماغ والأعصاب وتحت إشراف الدكتور محمود العبدالله عم نشتغل على cohort study هدفنا إنه نثبت الeffectiveness تبعت بينين ديفايس بحيث إنه نقارن الكونتراكشن عند هذا البيشنت قبل وبعد استخدام بينين ديفايس. هدفنا كمان إنه نشوف السايكولوجيكال aspect لهدول البيشنتس، لأنه إحنا من خلال الكويشنير اللي حطيناه سألنا هدول البيشنت إيش كانت حالتهم النفسية لما تشخصوا إنه عندهم فوت دروب، ورح نسألهم كيف حالتهم النفسية بعد ما يشوفوا في solutions زي بينين ديفايس. أما بالنسبة للفيوتشر بلان هدفنا إنه ما يكون بينين ديفايس بس مقتصر على مرضى الفوت دروب، هدفنا إنه يكون الجود سولوشن لأني paralyzed muscle in the body. Next. أما our achievements قدرنا نحقق المركز الأول في مسابقة مركز الريادة والابتكار بالجامعة الأردنية، بالإضافة إلى المركز الأول في مسابقة مؤسسة حكيم للحوسبة الصحية. هدف بينين إنه يساعد فرح وكل شخص عنده فوت دروب إنه يرجع يمشي and to eliminate disability.
هسه احنا راح نحط الكيو ار كود. تمام، طلعوا موبايلاتكم. الرانك راح يكون من 10 من ويك لاكسلنت. اول ما تفوتوا على الفورم راح تلاقوا 10 نقاط بالاول عن المعايير الكرايتيريا اللي على اساسها راح تصوتوا. تمام، بتصوتوا بس على اول سيكشن بتلاقوه، وتقريبا معكم 2 minutes يعني بالفورم.
يعطيك العافية أسيل. Before the lunch break, if you finish the evaluation, لازم أعمل بس quick appreciation certificate لدكتورة ضحى، دكتورة سيرين، ودكتور عمر. يعطيكم ألف عافية وشكرا على حضوركم.
Thank you.
محمد
تتكلم لو سمحتي.
دكتورة سيرين. Last but not least, Dr. عمر رواشدة.